Hey folks, welcome to another set of Chemistry 1 video notes. Today we're going to be talking about electrons in the periodic table. Specifically, we're going to learn how to write the full and noble gas electron configuration of an element, determine its valence electrons, and relate this to its position on the periodic table. We're also going to learn how to use the periodic table as a model to predict the relative properties of elements based on the pattern of valence electrons and periodic trends. Let's get started. First off, let's talk about why we're interested in learning about these electrons. The reason you can see objects in this world is due to visible light bouncing off of those objects. Sunlight, a type of white light, consists of all of the colors of light. We know this because when we shine white light through a prism, it splits up into a full spectrum rainbow. When we see the beautiful colors of fireworks, it's important to respect where those colors come from. There are all sorts of compounds that make these pretty colors when they're generously heated. For instance, strontium nitrate makes the red lights in fireworks, and barium nitrate makes the green lights in fireworks, etc., etc. The explosives within the fireworks are what allow these colors to shine. This is the same thing that happens with those packs of sticks that you can throw into your campfire and it changes the color of the flame. When the fire or these explosives give energy to these types of compounds, their electrons absorb that energy. They get excited and they go back to their resting state. When they go back to their resting state, they release that energy as different colors of visible light. The same exact thing happens when we look at what we call neon lights. We run some high voltage electricity through a sealed tube filled with neon gas, and neon's electrons get excited, fall back down to their ground or resting state, and release a bright red light. If we were to put that red light through a prism, it would not split up to give us a full spectrum rainbow like white light does. It does, however, split into distinct lines of reds and oranges. Other colors of these gas lights are made from different gases, so the phrase neon lights is kind of a misnomer, since only the red lights are made with neon. Here's an illustration of the full electromagnetic spectrum. Clear to the left, the highest energy waves, we have the gamma rays, which we just learned about in the last lesson. Clear to the right, the lowest energy waves, we have radio waves. And somewhere in the middle, a small sliver of electromagnetic radiation is called visible light, with violet being the most energetic and red light being the least. When we talked about Bohr's model, we threw around the word quantized, saying that Bohr described his electrons as quantized, or having only very specific energies. Each element is built a little bit differently, and its electrons can move between those energy levels that exist for the electrons. When it moves between those energy levels, it absorbs or releases this electromagnetic radiation. When it releases that energy, it releases it in the form of visible light. Each element only emits very specific wavelengths or energies or colors of light, not the full spectrum rainbow. This is called the element's atomic emission spectrum, and it looks like this. Atomic emission spectra are like fingerprints for an element, since no two elements are alike in their electron energies. Anyway, long story short, I know, already too late, all of the pretty, colorful things we see in the world, and I suppose the not-so-pretty ones as well, are due to the electrons in our atoms having only certain specific quantized energy levels. We're going to talk about those specific energies today. To be a little more clear, and with a nice animation here, our atoms first absorb energy, which pushes an electron to a higher specific energy level. We call that an excited electron. When that electron falls back down to its original energy level, called the ground state, it releases that extra energy in the form of light. Since each atom has different energy levels, each atom emits different bands of light, or colors of light. If we think back to Bohr's first model, he stated that electrons exist in specific orbits, or shells. I like to think of them as layers. They each have their own specific energy to them. We call them by their principal quantum number, or principal energy level, known as N. The first shell, closest to the nucleus, is called the shell 1, or N equals 1 shell. The next one is N equals 2, etc. The larger that principal quantum number is, the further away from the nucleus that shell, or those electrons, are. The bigger the shell is, the more energy the electrons in that shell have. Each of these shells, according to Bohr, could hold up to 2 n² electrons. So if n equals 1, that first level, then it can hold 2 electrons, because 2 times 1 squared is 2. The n equals 2 shell could hold up to 8, because 2 times 2 squared is 8. As you continue to get further from the nucleus, these shells increase in energy, but the increase gets much smaller each time. For instance, the jump from n equals 1 to n equals 2 is quite large, as you can see on this chart. From n equals 2 to n equals 3, that gap is much smaller. This becomes important for when Bohr had to revise his model, as he started working with elements more complicated than hydrogen. Bohr's revised model simply split each of these shells into smaller shells called subshells. There are 4 types of subshells: the S, the P, the D, and the F. The S subshell exists in all principal energy levels. The P subshell exists only in principal energy levels 2 and above. D exists in 3 and above, and F exists in 4 and above. Any S subshell can hold up to 2 electrons max. The P subshell can hold up to 6 electrons, the D subshell can hold up to 10 electrons, and the F subshell can hold up to 14 electrons. You still get the same maximum number of electrons in each principal energy level, even when we split them up like this. For instance, n equals 1 only has the 1s subshell, which holds 2 electrons, since it's an S subshell. In Bohr's old model, n equals 1 also held only 2 electrons. In the n equals 2 energy level, we have a 2s and a 2p. These can hold 2 and 6 respectively for a total of 8 electrons, just like Bohr said the first time around. Try that out on your own for the third energy level. How many electrons can a 3s, 3p, and 3d subshell hold in total? As you can see, as we get further from the nucleus, some of these subshells begin to overlap in principal energy levels. For instance, the 4s subshell is slightly lower in energy than the 3d subshell. This is the exact reason that Bohr had to make these changes to his model. That weird ordering of energy levels is what happens in real life, but his old model couldn't explain that. At this point in the video, if you've been listening, go ahead and pause the video, then draw the best, most creative smiley face that you can in the far outer edge of your notebook page that you're on. Be sure to make it prominent enough that I'll notice it when I grade your notebooks. The order of the energy levels these electrons fall into is extremely important for later discussions about how the atoms will bond, since the outermost electrons, or valence electrons, are the only ones that participate in chemical bonding. To help you remember that order, you could use any of these 3 methods. This chart is super easy and a quick shortcut that people have used for years. Simply write 1s, then 2s, then 3s, etc., all the way to 7s in one up and down column. Then, skipping the 1, going straight to 2, do the same for 2p, 3p, etc., all the way to 7p. Do the p column just to the right of your s column. Then do the same for your Ds, but starting with 3. And finally, you can do the same for the Fs, but only starting with 4. You could omit the 6F and 7F subshells since we don't use them. Then to figure out the order, we simply start on the top right and draw an arrow to go down. Once we run out, we start back on the next, just under the top right, and go down again. So the first arrow goes through 1s, the second arrow goes through 2s, the third arrow you'll draw, just follow these arrows on this chart, will hit the 2p and then the 3s. And then it'll go to 3p, 4s, 3d, 4p, 5s, etc., etc. If you can remember how to draw that chart and how to draw those arrows and just follow the order through, that's probably the easiest way to remember it. On occasion, you'll also have this handy-dandy chart available. This chart is an energy diagram that shows us all of the subshells as a line, and they're put together on there relative to how much energy they have. So the least energy is at the bottom and the most energy is at the top. When we fill these diagrams up with electrons, we always start with the 1s, or the one at the very bottom, and work our way up. Now, the real trick is to recognize the geniusness and beauty of the way the periodic table is organized. We'll discuss it a little bit more in depth together in class, and maybe a little more in this notes video, but take a gander at this periodic table now and see if you can recognize the pattern. Maybe after we do some electron configurations, go back and look at this periodic table again to see if you can see the pattern then. One thing you might notice immediately is that for the S and P subshells, the principal quantum number, that big number before the S or P, is the same number as whatever numbered row or period that element is in. This will become important for later. We could fill in electrons on those models that we had drawn before, but that'll get a little bit tedious and it's a little inconvenient to have to draw those atoms each and every time we're talking about the electron configuration. So, as lazy chemists, we've come up with a much easier way to write how these electrons are arranged, and we'll call it the electron configuration. The first step to writing an electron configuration is to determine how many electrons you have. For atoms, it's the same as the atomic number. For cations, you take away one electron for each positive charge on the ion. For anions, you add one electron for each negative charge on the ion. Then, once you know the total amount of electrons, use the periodic table, the first shortcut chart we talked about, or the energy diagram on the bottom right of the previous slide to fill your electrons in the empty spaces, starting at the lowest energy, or the 1s subshell. Remember, S's hold up to 2 electrons, P's hold up to 6, D's hold up to 10, and F's hold up to 14. Place your electrons in the 1s until it's full, then move on to the 2s, and then the 2p, etc., etc. Keep doing this until you've run out of electrons. To write the configuration, we simply write down all of the subshells that have electrons in them. Then to the top right of each subshell, we write a little superscript that tells us how many electrons are in that subshell. So, for example, if we're looking at carbon, carbon's atomic number is 6, which means as an atom it has 6 electrons. Start by placing 2 electrons in the 1s subshell, then 2 electrons in the 2p subshell. We've now used 4 of our 6 electrons, so we have 2 left to place in the next highest energy subshell, which is the 2p. This gives us an electron configuration of 1s2, 2s2, 2p2. Fluorine normally has 9 electrons, but if it's a negative anion, like stated here, that means it has 1 extra electron, so 9 plus 1 is 10. Do this the same way as we did carbon, and we'd get 1s2, 2s2, 2p6. Titanium, with an atomic number of 22, would give us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Writing out the electron configurations this way is super important so that we can determine how many electrons are available to participate in bonding. In other words, how many valence electrons there are. To determine that, you simply look at the subshells with the highest principal energy number and add up all of their electrons together. So for carbon, n equals 2 is bigger than n equals 1, so looking at just the 2 subshells, the 2s and the 2p, we have 2 electrons in each for a total of 4 valence electrons. For the fluorine -1 ion, the second shell is still the highest in number, so we add 2 plus 6 to get 8 valence electrons. For titanium, the highest principal energy number here is 4. So we're only concerning ourselves with the 2 electrons in the 4s subshell. Even though it's not written furthest to the right, we only focus on the principal energy number that's the largest. A quick review of the periodic table. The left and right rows are called periods. The up and down columns are called groups or families. Each element square has an atomic number, an atomic mass, a symbol, and a name for the element. Here are all of the electron configurations for the first 4 alkali metals, or metals in group 1a of the periodic table. Notice something about them? They all end in an S1 subshell. In fact, they all even have only 1 valence electron. Maybe that's a fluke. Let's look at another group. Here are some of the alkaline earth metals, or elements in group 2a. They all end in an S2 subshell, giving them 2 valence electrons. Wow, is this on purpose? One more. How about the halogens? They all end in S2 and P5 subshells, giving them 7 valence electrons. We also happen to call this group Group 7a. Here's where we can see the pattern. All group 1 and 2a elements, including helium as well, make up the S block of the periodic table. All these elements end in either S1 or S2. This S block happens to be 7 elements tall and 2 elements wide. The whole right chunk of elements, groups 3A to 8A, or 13 through 18, excluding helium, make up a 6 high, 6 wide block of elements that all end in a P subshell. We call this the P block. The D block is the middle section of transition metals that make up a block about 4 high and 10 wide. You might recall that the D subshell holds 10 electrons at most, and the D block happens to be 10 elements wide. Are you seeing the pattern yet? And finally, all the elements that end in an F subshell can be found in the lanthanides and actinides, the 2 odd rows that we pull out and place at the bottom of the periodic table. These are 2 high and 14 wide. So, here's our periodic table again. Can you look at these elements and find their electron configurations? You just start with hydrogen on the top left, and then work your way across and down. Let's try this with carbon, one we've already found the electron configuration for. We start with hydrogen clear up on the top left, and it's next to helium. That's the 1s1, 1s2, so we filled the 1s row. Next, we go down to the next row, and we have the 2s block. There's 2 elements there, and we pass right through them, so we end up with 1s2 from here, and then 2s2. Next, we go over to where boron is, the beginning of the 2p block, and we get 2p1 and then 2p2. Carbon is the second spot in the p block. So our electron configuration is 1s2, 2s2, 2p2, just like we got before. What about copper? Same idea. Instead of stopping on carbon, go straight through the whole row all the way to neon, giving us 2p6. Then go down to sodium and magnesium for 3s2. Then on the third row, keep going straight through the P block and you get 3p6. Go down to the fourth row, you go through 4s1, then 4s2. So just taking stock of what we have so far, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Finally, to get to copper, we've got to go 9 elements into the D block on the fourth row. The D's are 1 minus the row number, so it's actually called the 3D section. So we go 9 elements into the 3D section, and we end up with 3D9 as the last bit we write down for the electron configuration. It's also important to note that the F section is 2 less the row that it happens to be in. So in period 6, we run into the 4 Fs, and in period 7, we run into the 5 Fs. We can also write down an abbreviated version of the electron configuration known as the noble gas shorthand configuration. Basically, we look for the noble gas that comes before the element in question. So in copper's case, that would be argon. Argon's electron configuration ends in 3p6, since it's the sixth one over in the 3p section. So 3p6 and everything before that from copper's electron configuration could just be replaced with the symbol for argon placed in brackets. The first and most obvious bit of information, since we already talked about it, is that our elements have the same number of valence electrons if they're in the same group or column on the periodic table. We'll use that information a lot in our upcoming lessons. Next, and also fairly obvious at first, is that as we go from top to bottom in a group, our atoms get larger. Remember how we said that the principal energy number corresponds to the row number, or the period number? As we go down in a group, we add shells, or layers of electrons, which makes our atoms significantly larger. As we move from left to right, say from sodium to chlorine, we increase the number of protons in the nucleus, but we stay in the same outer layer of electrons. The increase in protons increases the attraction from the nucleus to our outer layer of electrons, causing those electrons to be pulled in a little bit closer to the nucleus. So, in short, our atoms get very obviously larger from top to bottom, and they get a little bit smaller from left to right. Or in a shorter way to remember it, all the way at the bottom left is the biggest element, francium. If you can remember the trend for atomic size, you can remember all of the rest of the trends by using a little bit of logic and critical thinking. Next up is the periodic trend for reactivity. We'll hit on this a lot more in the next few lessons, but simply put, the goal of any atom is to look, at least valence electron-wise, like a noble gas. They do this by gaining or losing electrons to get to 8 valence electrons, or outer shell electrons. This is known as the octet rule. Atoms that only need to lose or gain 1 electron, such as those in groups 1 or 7 with 1 or 7 valence electrons respectively, are much more reactive than those that need to lose 2 or 3. In general, elements to the left of carbon lose electrons to get to an octet, and those to the right of carbon gain electrons to get to an octet. Beyond that, if I'm trying to lose an electron, like those on the left side of the periodic table, that's much easier to do when my electron is super far away from my nucleus, as in the case for the elements in the bottom left of the periodic table. If I'm trying to gain or attract a new electron, that's a lot easier when my nucleus is really close to the outside of my atom. So these smaller atoms on the top right corner, like fluorine, have a much easier time adding an electron to them than those on the further down level. Ionization energy is the amount of energy it takes to remove an electron from an atom, turning it into an ion. Basically, the smaller your atom is, the harder it is to pull an electron away from the atom. Therefore, the smaller the atom, the greater the energy required to remove an electron, or the larger the ionization energy. In the same general direction, electron affinity describes how likely an atom is to gain an electron. Those smallest elements in the top right, like fluorine, tend to be better at gaining electrons than those on the bottom left. As your atom gets smaller, it becomes easier for it to pull in an extra electron. Notice we ignored the noble gases here. Noble gases already have 8 valence electrons, so they don't want to add or lose any of them. Finally, the last and most significant one we'll use this year is electronegativity. This describes how strongly an atom will pull shared electrons toward it while it's bonded to another atom. When 2 atoms are sharing their electrons between them, which we'll discuss more in depth in the next lesson, those electrons may end up more toward one atom than the other. They might not be shared equally between the 2 atoms. This occurs when one atom is much more electronegative than the other. Think of it like a tug of war, and the electronegativity value is the strength of that atom. The higher the electronegativity of the atom, the more those electrons get pulled toward the atom. This again gets larger as you go up and to the right, because the atoms are smaller and can attract those electrons ever so closely to it. We also ignore the noble gases here since they rarely participate in bonding. Well, that's all for today, folks. As always, if you have any questions, please ask.